Hello, future engineers, subscribers, viewers, and students. Here is the fifth or the sixth. This is the sixth way of solving beam deflections on beams. This problem here, which I already solved by 5 methods. So this is the sixth method by the three moment equations. So the beam is subjected to the loads shown. If EI is constant, determine the slopes and deflections at points A, B, C, D, and E by the three moment equations. So this is the deflected shape and the reactions from the previous methods, or you can check this by your own because this is a determinate beam. So this is the three moment equation when E is constant and I is different for each segment in general. So moment at A, L1 over I1 plus 2 times moment at B, quantity L1 over I1 plus L2 over I2 plus moment at C, L2 over I2, then the value of 6 area 1A over I1 L1, which is 6 over L over moment of inertia. Area 1A is the moment of area in portion AB with respect to A, and 6 area 2B over I2 L2, 6 over I2 L2, when area 2B is the area between B and C. Moment diagram by parts by treating each segment as simply supported, then with respect to point C. So that's the meaning. Then 6 EI times quantity HA over L1. This is the vertical distance of point A from the reference horizontal line through B. So for example, if we consider ABC, then this is the horizontal line through point B on the elastic curve, then this should be HA. So HA, then this is the vertical distance from the horizontal reference through point B on the elastic curve to point C is H sub C. So that's the meaning of that. So the moment at point B is, if you consider AB and take moment about B, it is just positive 107 over 3 times 3. So clockwise moment positive equals counterclockwise moment. Counterclockwise is positive moment if that point is right portion of the segment being considered or isolated. That's why moment at B is 107 over 3 times 3, because if it is clockwise, it is equated to counterclockwise moment, which is positive. So positive 107 kilonewton meter. Then, if we want to compute the moment at C, so summation moment at C, this should be clockwise plus 15 times 5 clockwise equals counterclockwise moment 353 over 6 times 3. So computing for M sub C is 101.5 kilonewton meter. So first we consider ABB, and this is the reference line through B. Therefore, if this is delta B, then HA would be delta B. H sub B is also delta B because the reference is the horizontal line through the middle point B. So HA is delta B, H sub B is also delta B. Moment at A is 0, moment at B is 107 kilonewton meter, and the moment at B is negative 15 times 2, so negative 30 kilonewton meter. So I'm not showing it, but we can easily compute the moment at B to be negative 30, negative 15 times 2. So substitute into the guide formulas, moment at A 0, plus 2 times moment of B, quantity L1. L1 is the length of AB divided by moment of inertia. Because moment of inertia is constant, we just treat this as 1. I1 and I2 equals 1. So, over 3 times 3 over 1 plus L2, that's the distance between B and B, because we consider A, B, B. So, L1 is distance or length of AB, L2 is length of BB, which is 6. Then plus moment at D, which is negative 30 times L2, 6, plus 6 area 1A over L1. There's no load in portion AB, so there's no value 6 area 1A over I1 L1. Then in BD, there is this load there. The formula is integral of differential P times B. B is the distance of the centroid of the strip from the right support, from the right point rather, which is, if we call this X, then this distance is X. This distance B is X plus 3. While A is supposedly this distance, which is 6 minus X. That is A, if there is 6 area 1A over L1 I1. But there's none, so it is just 0. So therefore, for 6 area 2B over I2 L2, the formula is, the guide formula is PB over L, quantity L square minus B square. Since there's no P, it is imagined as the differential P, and the differential P is the area of this strip, which is W dx. So this is dx, where W is solved by similar triangles. If that entire height is W, then this is W minus 15 for this right triangle here. So W minus 15 as 2x equals 30 minus 15 is 15 kilonewton per meter as to 3. So that's why W is 5x plus 15. So we have here integral from 0 to 3 for the variation of x. Then W dx, differential P, W dx, 5x plus 15 dx. Then B is the distance of the centroid of the strip from the right point B. So that is x plus 3 or 3 plus x divided by L of BB, which is 6, quantity L square, 6 square minus B square. And B is x plus 3 squared. And limit 0 to 3. Then there is a concentrated load. So PB 12 times B 3 all over 6. Quantity L square, 6 square minus 3 square. L of portion BB. Then equals 6 EI. So again, the distance of A below or above the reference horizontal line through B is HA, but HA is equal to delta B, and H sub D is also equal to delta B. So delta B over LAB, which is 3, plus delta B HD all over LBB, which is 6. So simplifying, this value is 1926. This is negative 180. You can easily compute that. The value of the integral 64.5. The value of this expression is 162. And this is 6 EI times delta B. So computing for delta B is equal to negative, because delta B is, the result here is positive, but the reference is, the actual reference is the horizontal line through the origin, which is A, which is the horizontal axis of the beam. So B is below the horizontal axis, therefore we just put the sign, which is negative 847.5 over EI, because B on the elastic curve is below the x-axis. That's why the result here is positive, and the meaning of positive is A is above the horizontal line through B. But B is below the x-axis. So that's why it is negative. Then, next, let's solve for theta A. And this, to solve for theta A, we draw the moment diagram by parts between A and B. And it is just a triangle, this part here. So 107 over 3 times 3 is 107 over EI. So this is the area of the moment diagram by parts between A and B. Then we compute the division of B relative to the tangent at A, because take note, the three moment equations, the derivation of the three moment equations is based on area moment. So that's why we can use area moment in computing the slope theta A here. So let's solve this value because we already found delta B. So that is just the area between, the moment of area between A and B with respect to B, because we are computing division of B relative to A. And that is 1/2 of 3 times 107 over EI times 1. It is positive. So that means the point B on the elastic curve is above the reference tangent at A. So it is 160.5 over EI. But based on the figure, the slope at A is negative, and tangent of theta is equal to theta A itself, because theta A is small, very small, that the tangent of the angle is just the angle itself. So again, theta A is negative, it is opposite over adjacent. So let's just make the opposite combined value negative, and that is negative delta B, negative 847.5 over EI, and another negative of deviation of B relative to A, negative 160.5 over EI, then divided by 3, because the entire distance or this leg here of this right triangle is 3 times theta A. Solving for theta A, it is negative 336 over EI. So next, we consider the portion. There is no delta B here, but we can compute delta B by drawing the tangent at B. Then we may compute deviation of A relative to the tangent of B. Then from there, we compare deviation of A relative to the tangent at B against delta B, so that we can set up the formula for the slope at B. So to continue, let's consider ACD as the 3 points in setting up the three moment equations. So moment at A is 0 plus 2 times moment at C. The moment at C is 101.5 positive. Then AC is 6 over I1, which is just 1, plus LCD, which is 3 over 1, moment of inertia, plus moment at D, negative 30, times L2, which is 3, plus moment at, of course, 0. Then plus the value of 6 area 1A over L1 I1, so 6 area 1A, and that is equal to integral of differential force times A. A is the distance of the strip from A over L, quantity L squared minus A squared. So integral 0 to 3 of differential t, which is w dx, and w is 5x plus 15. So dx, distance of the strip from left is, which is a, small a, and it is equal to 6 minus x divided by L, quantity 6 square minus a square, then plus, there's no value of this because imagine this is a simply supported beam from A to C, and this load 12 kilonewtons is over the support, so it will not produce moment. It will not produce moment because the reaction over the support is also 12 kilonewtons. So it will not bend the beam AC, in other words. So that's why there's no value PA over L, quantity L squared minus A squared. There's no also value PB over L, quantity L squared minus B squared for that load. It acts as the support. Then for portion CD, there's no load, so that's why it's just 0. Then equals 6 EI. So this is the horizontal line through the middle point, which is C, and the distance from point C on the beam to this elastic curve is delta C, the deflection. Therefore, HA is equal to delta C, and HD is also delta C. So we have 6EI quantity HA, which is delta C over 6, plus HD, which is also delta C over L2, which is 3. So simplifying, this is 1,827 negative 90. The value of the integral is 5859 over 8. And this is 3EI delta C. So computing for delta C is negative 823.125 over EI. Then we compute EI division of point C relative to the tangent at D, and it is represented by this. If it is positive, this is true because in this figure, the point C on the elastic curve is above the reference tangent at D. So we draw the moment diagram by parts between C and D, including the moment of this 15 here because it will cross this portion CD. And this is the moment diagram. 353 over 6 times 3 is 176.5 over EI at C. Then the moment of the 15 kilonewton load, 15 times 2 is 30 over EI. 15 times 5 is 75 over EI. So just concentrate on these two areas. So it is 1/2 positive 1/2 3 times 176.5 times moment arm 1. We take moment about C. Then plus we divide this trapezoid into two triangles. For the small triangle, 1/2 of V times 30 over EI. Moment arm is 2. And for this bigger triangle, 1/2 of 3 times 75 over EI. Moment arm is 1. So computing, it is positive 62.25 over EI. So since it is positive, and this is correct because point C in the elastic curve is above the reference tangent. Based on the figure, the tangent at D has a positive slope. Then, therefore, theta D, the whole of this value is 3 meters, so 3 times theta D. So we equate 3 theta D to delta C and division of C relative to D, treating this as positive because the slope at D is positive. You look at the tangent. So 3 theta D is equal to delta C, which is made positive, to 3.125. That's delta C. After we compute this, then plus division of C relative to D, 62.25 over EI. The value divided by 3, so we can compute theta D 295.125 over EI. So for theta b, we have to draw or consider the moment diagram between A and B, and let's evaluate the deviation of A relative to the tangent of B. So this is the only area between A and B. So deviation, EI deviation of point A relative to the tangent at B is the moment of this area with respect to A. So area 1/2 of 3 times 107, the moment arm is 2/3 of 3, so 2. So deviation of A relative to B is 321 over EI. So that's why the tangent at B is above the horizontal, because this is only 321 over EI as compared to delta B, which is the magnitude is 847.5 over EI. So that this in this right triangle, this angle is theta B. The angle between the horizontal and the tangent at B is theta B. So in this right triangle, the opposite is 3 times theta B. And because theta B is expected to be negative, it lies in the fourth quadrant where the slope is negative, or in the second quadrant, slope is negative. So this 3 theta B here is equated to a negative value. And that negative value is the negative of the difference between absolute value of delta B and deviation of A relative to B. So take note that if we treat all this as positive, deviation of A relative to B plus 3 times theta B equals delta B. Therefore, 3 times theta B is delta B minus deviation of A relative to B. But we just make this negative. So negative absolute value of delta B minus absolute value of deviation of A relative to B. So that is 3 theta B is equal to the negative of absolute value of delta B minus absolute value of deviation of A relative to B. And computing for theta B, it is negative 175.5 over EI. Then for delta E, which is this, we write 3 moment equations, this time between between considering the span A, B, and E. So AD is 9 meters long, while DE is 2 meters long. The horizontal reference line is now through D, and this is the horizontal axis beam or the x-axis. So see this horizontal reference line through D will cross point A, therefore HA is 0. And this is now the horizontal line, and we expect that this is point E expected, or you may assume that it is above the horizontal x-axis, so that HE is positive, as shown in the figure. So 3 moment equation on ADE, the moment at A is 0, plus 2 times moment at B is negative 30, times quantity LAD over I, so 1 I is just 1, I2 or I in BE is also 1, where LAD is 9, so 9 over 1, plus LDE 2 over 1. Moment at E is 0, then plus 6 area 1A over L1, so the 6 area 1A over L1 is this expression here. So the moment of differential P with respect to moment arm. This is differential P, W dx. W is 5x plus 15. Integral 0 to 3 of 5x plus 15 dx. That's dt. A is the distance of the centroid of the strip from A, and that is 6 minus x, 6 minus x, divided by L of AB, the quantity L squared, 9 squared, minus A squared, 6 minus x squared. That is A, that is A squared. Then plus, this time 12 is on AD, so the formula is PA over L, quantity L square minus A square. So 12A is 6 over L 9. Quantity 9 square minus 6 square. That's it. So 0 for 6 area 2B over L2, because the load, if this is a simply supported beam, the supports are at D and E, and the 15 kilonewton load is over the support, it will not bend the beam, so there's no value for 6A2B over L2I2. Then equals 6EI, quantity, as I said, HA is 0. The horizontal line through the process A, so HA is 0, so 0 over 9. Plus HE, this is point A, assume above E, and that is delta E also, delta E over L2. So the value of the integral, 1950.75. This expression is 360. Then this one is 6 EI delta E. So computing 1950.75 plus 360, then divided by 3, we obtain delta E equals 550.25 over EI. So that's also the sign, because point E is above the horizontal axis, x-axis, or the beam's axis. Then finally, to solve for theta E, this is the tangent theta E. And let's evaluate this distance of D relative to the tangent at E. So we compute EI division of D relative to the tangent at E. So it is just the moment of this area between D and E. This is D, this is E, this area here, with respect to D. So it is area 1/2 of 2 times negative 30. Moment arm is 1/3 of 2 or 2/3. So it is negative 20 over EI. Division of D relative to E is negative because point D, which is this on the elastic curve, is below the reference tangent at E, as shown in the figure. But this vertical deviation of D relative to E, the magnitude is less than delta E, which we have just computed, 550.25. And the slope at E, therefore, is positive. It is sloping up to the right or down to the left. That's positive. This vertical distance of vertical leg of this right triangle, if this is theta E, this is also theta E, the angle between the horizontal and the tangent at E, then this is 2 meters, so that's why that is 2 theta E. So this 2 theta E is equated to this vertical leg of the right triangle, which is treated positive because theta E is positive. And that is equal to delta E minus deviation of D relative to E, which is treated positive, so that this is positive also. So that is 2 theta E is equal to the absolute value of delta E, 550.25, so it is still 550.25, minus the deviation of D relative to E, and the absolute value of negative 20 over EI is positive 20 over EI. So minus positive 20 over EI. Solving for theta E is 265.125 over EI. So that's it for this video.